Okay, so like the t-shirt says, I'm not insane, just mostly. So I work for Red Hat. I spend most of my time working on XFS and VFS level stuff, mostly in the upstream kernels. What I'm going to be talking about today is the developments that's been made in XFS scalability, mostly to do with metadata, because that's been the traditional weak point of XFS. We all know that it scales to massive amounts of data, but if you can't create that data really fast, lots of files and so on, then it doesn't really help you all that much. That's where metadata scalability comes in. Once we've gone through that, we're going to talk about what's going to happen in the next couple of years in terms of XFS development and scalability there. And really the challenge for scalability these days is reliability, and it's not performance. We fixed the performance problems. So, go back to LCA 2007 and Valorora, when she was describing when do you use XFS. If you have lots or large, use XFS. There's a problem with that though. We have metadata performance problems. This is what we're going to talk about. What are they? How do we solve them? Now we've solved them, how well does XFS scale on metadata intensive workloads? Where are we going to go from here? Why are we changing the on-disk metadata format? That might seem a bit drastic, so we'll explain it. And then what does it all mean? Okay, so the XFS metadata problems. Metadata read scales very well in XFS. Everything is B-tree structured, so it's logarithmic lookup time. It's very scalable. However, metadata performance is just terrible. Okay? We get excellent parallelism through the metadata transaction engine, but the problem is that the transaction commit basically serializes, and it's the big problem. Okay? It won't scale past one CPU. Generally, that's because of the limitations in the I/O level, not that there's a lock in the way. We'll get to that. Because the transaction throughput, the commit, is limited by the journal bandwidth. We're writing so much information, so much metadata into the journal that will basically max out the bandwidth of any disk subsystem that you have. And that's not with data, that's with just the journal. A further problem is that metadata writeback causes I/O storms. We're modifying so much metadata and it's spread all over the disk. We then end up with random writeback patterns. 4K writeback here and then over there, and we seek the disks to death. So even if we were to fix the journal bandwidth problem, we've still then got the problem of metadata writeback being the limitation. And then of course with XFS, there's lots of locks to deal with. Okay, so really, it can't be that bad, can it? Everybody says lots and large, How bad really is it? So, these were taken on a 2634 kernel, single SATA drive. FSMark creating basically the same workload that Avi was talking about. FSMark creating zero-length files. One directory per file, so there's no contention at the VFS level or the file system level. Okay? Well, there's supposed to be no contention at the file system level. And what we're seeing here is the result versus the journal throughput. So our result is on your right-hand side, and the journal throughput is on the left-hand side. As we can see, the journal throughput's at 120 megabytes a second. That's as fast as that SATA drive would go. And the results scale directly with the journal throughput. So let's go to a faster drive, just to show that that holds true for even larger storage subsystems. Okay, we've now got 40,000 or 45,000. It's 7 or 8 times faster than that previous disk. Well, there should be. There's 12 disks there. Journal throughput is up at 550 megabytes a second. That's all that system was doing, was writing to the journal. Now, I know most of you don't have drives that do 550 megabytes a second. So this is a big problem. And those that do have drives that have got 550 megabytes a second, you don't want the journal to be consuming that. That's just a waste of bandwidth. So let's compare that to ext4 on the same subsystem. So even with a single thread, we can see that ext4 is a lot faster. And part of that is to do with the CPU usage. because of the algorithms that XFS has, they're a lot more complex than ext4. There has to be some trade-off for the scalability that the file system has. So any modification has to do a lot more work, and as a result, the per CPU throughput is actually a lot lower, even when there's no limitations. Now you can see this holds true. Up to 4 threads, yeah, X4 is a lot faster. 8 threads look a little bit different. We'll come back to that one. But as we saw from the previous slide, XFS is limited by the journal throughput there. Okay, so it looks pretty bad. In real-life workloads, ext4 can be 20 to 50 times faster than XFS when there's file data also being written. Untarring a kernel tarball is the classic metric for this sort of thing. There's systems like a single SATA drive where ext4 takes 3 or 4 seconds to untar the kernel tarball, and XFS is taking 60 seconds. And then overwriting it, ext4 is taking 10 seconds and XFS is taking 2 minutes. It's pretty bad, pretty slow. This is the state of XFS in 2009, early 2010. Realistically, unless you have some seriously fast storage, XFS just doesn't perform all that well on metadata modification intensive workloads. Okay? And that's pretty important when you're talking about storing a couple of billion files in your file system. You have to be able to create them somehow, and you want them to be able to create quickly and so on. But, I mean, it wasn't all bad. I mean, we're seeing ext4 having some problems with those workloads as well. So some of these problems may not be just XFS, though it turns out that they were. So, the fix is in. What I'm now going to talk about is all the changes that have been pushed into the kernel since 2.6.35 and over now to the 3.3 merge window, which has actually removed old code that some of this stuff replaced. So what we had is a major algorithmic change. There were a lot of optimizations to do, mainly because there were lots of locks and structures that were suddenly hot because of the algorithmic change. But we managed to do this with no on-disk format changes. So while we were developing it, we were able to turn these features on and off with a mount option. Even a remount. They could be done dynamically because there was no change to the on-disk format. So the major algorithmic change that we're looking at is this thing called delayed logging. So the idea was originally floated in back when I was working at SGI, and we were doing XFS architecture meetings and having all big powwows and blue sky events to try and work out what we're going to do for the next couple of years. So Nathan Scott, some of you may know him. He was the XFS maintainer for quite a while. He's not here. He's normally here at Linux.conf, but he's not this year. Yeah, he came up with this idea. And it wasn't anything groundbreaking. It was basically saying, oh, ext3 is doing this. We should do this. Okay, sounds simple. But actually implementing it is kind of difficult. It took me 4 goes over 5 years to actually come up with a working solution. Every time I tried it, I came across some other show-stopping problem. Deadlock here, or an unsolvable deadlock, or memory allocation could fail here, and that was it. We're dead. Wouldn't work. But the eventual solution that was implemented came from considering a different problem. Another reliability problem, if you want. Transaction rollback. In the, oh, well, then maybe we've got to copy some data before we actually modify it, so if the modification fails, we can roll back to what was before. Okay, so we've got to copy the data. Okay, that's easy to do. But we don't want to copy all the data that we might modify, because that's a lot. An XFS transaction, if you're using 4K block size file system, an XFS transaction could modify 300 or 400 kilobytes of metadata. If you've got to allocate that and copy it before you even start doing any modifications, that's quite a lot of overhead. So I started thinking, oh, well, we'll copy the data at transaction commit time, just the dirty data, because we know exactly what we modified in the transaction. Oh, and then we store it. Hey, hold on. Lightning struck. I realised that all of the locking problems and everything went away if we copied the data at transaction commit time. We didn't have to relock when we wanted to actually journal the changes to disk, to then copy the modifications out of the object in memory. So all of a sudden, We've got a solution to this problem we've been trying to work out how to solve for 5 years. And basically, it comes down to aggregating transaction commits in memory. So, if we're aggregating the transaction commits in memory, then, well, there's a problem there, isn't there? You crash, you know. Well, they're not on disk. That's exactly it. So sometime we've got to checkpoint them. Checkpoints were basically a new transaction type. We add transaction types every so often. It's just a new hash define. We already had all the structures on disk to handle it, and suddenly we've now got this transaction with all the aggregated transaction commits that might have 100,000 changes in it. But the thing is, those 100,000 changes are 100,000 unique changes. What we were doing previously is that every time we change an object, say a directory block, you create a file, you've got to write a new entry into the directory block. Okay, we write that modification down into the journal. Okay, we create another entry in the directory. We write that modification down into the journal. It's the same block. But because the journal hasn't gone to disk yet, we have to relog the other changes that are in memory so that we know that all of those changes that we've been aggregating get to disk in the one change, in the one transaction. So as we keep modifying the directory block, we start logging it again and again and again and again, and the amount we log increases. So in a single journal buffer, we might relog a directory block 5 or 6 times, and then we've run out of space and we've got to write it to disk. This is how we end up with writing 550 megabytes of data to disk, or sorry, metadata to disk in the journal. What delayed logging does is it just keeps copying them into an in-memory buffer, and they don't get written to disk. And later on, when we've got enough space, you know, we've used enough space, or you know, we're running out of space in the journal, or somebody does an fsync, we take everything in memory and then write that into the journal. Oh, excuse me. We write it once, not every time it's modified. And the result is what we're aiming for, an order of magnitude reduction in journal throughput. Suddenly that 550 megabytes a second of journal throughput is down around 30. And we're going twice as fast because we can do a whole lot more because we're not I/O bound. The best part about it is it uses known algorithms. We're basically stealing a technique that ext3 has used for years. We know it works. We don't have to do any sort of formal mathematical proofs for some new magic journaling technique because we have experience with it and we know it just works. If you want to know more about it, it's all documented in the kernel. Funny that, we document our designs. Novel idea. In 3.3, this is the only journaling method that's supported. In 2.6.39, it became the default. But in 3.3, we've removed the old code. So this improvement has actually had a net effect of reducing the amount of code in XFS. It goes a lot faster, the code is a lot simpler, and you know, we've got something for nothing, really. So there was a bunch of other improvements at the same time. Because we were doing delayed logging, everything else went faster. We're no longer bottlenecked on the journal. So for every transaction, we have to do a log space reservation so that we know that the whole thing will fit into the log when we go to commit it. We have to do that before we start the transaction. And then, of course, when we finish the transaction, because we haven't used all that space, we have to return it to the free space pool. So we've got to do 2 modifications to a log space reservation structure for every transaction. Now we're doing a couple of 100,000 transactions a second. That means that that becomes a very hot path when you've got a single global lock for the file system to protect those values. So that had to be fixed. That now is a nice and complex atomic compare and exchange loop that tries again when things go wrong. Oh, and it does still have a global lock on it in the slow path when there's things waiting and there's not enough space. So it kind of is complex. Too complex to explain here, except for the fact that I'll point out that the change in the algorithm exposed an 18-year-old bug in the XFS code. Yeah, almost as old as Linux is itself. So that was then solved. Now, I mentioned I/O storms earlier on with the metadata write-back. XFS had 3 methods of writing back metadata. It could do it synchronously, which it still can do. It could do it asynchronously, so you just fire it off and keep doing what you were doing. And then it had another method called delayed write, where it just put it on a queue and said, in 30 seconds time, write it out. And a background daemon would come along and do that. The problem we were having is that now that we've got so much metadata in memory that is dirty, when it comes to doing async write-back, we were just splattering stuff all over the disk. Oh, look, we've got a buffer to write it. And we've got a buffer to write it. And that one would go out over there, that one would go out over there, that one would go up there, and we'd seek the disks to death. It wouldn't go much faster without fixing that. So what we did is we removed async metadata write-back. We turned everything into delayed write metadata. Synchronous is still there, and that's used in only 2 or 3 places, but everything else is delayed write. And the trick we use now is that before we go and start writing any of these delayed write metadata buffers out, which there might be several tens of thousands of them in memory, we go and sort them in ascending disk order. So we do the work of the I/O scheduler for it. The I/O scheduler can only have by default, an outstanding number of I/Os queued of about 128. We've got 3 orders of magnitude more buffers sitting there trying to write them out. We can do a much better job of scheduling the I/O with that big wide window that we have compared to the I/O schedulers. So it makes sense to do it that way. It makes a really big difference because it now aggregates. The I/O scheduler now merges adjacent I/Os, and instead of doing random 4K I/Os everywhere, our metadata write-back starts to look like a bandwidth-bound problem, not an IOP problem. Makes a really big difference. So that's the sorting that we do. That's the reason why we do it. Now, of course, if we've got several tens of thousands of objects in a transaction commit, we've got to track them in memory somehow so that we know what's got to be written out when we run out of space to drive the delayed write metadata. So that's our active log items. Now, that's a single global list. It's an ordered list, which makes it an interesting problem to scale insertion and deletion of tens of thousands of objects rapidly while it's being hit by all sorts of other parts of the file system. So rather than try and completely redesign it, we've now got batch interfaces for taking a batch of objects with an identical index and just splicing them into the list. So we reduced log contention there by 2 orders of magnitude. No longer a problem. And now, of course, we've got so much more metadata going in and out of the system, we're getting problems of running out of memory and losing hot blocks out of the cache. Because we've got several 100,000 buffers in memory now that are active, rather than maybe a few thousand, maybe 10,000. Okay? We have a much bigger active metadata set in memory. We were using the page cache to cache it all, but we've got a very complex hierarchy of metadata that is all B-tree based. So if your reclaim algorithm throws the B-tree route out of memory, that's the one you're using all the time. You need to pull it back in. You've got to wait for it to occur. And so we need to actually have some form of reclaim algorithm that understands that you reclaim tree leaves before you reclaim tree nodes, and you reclaim inodes before you reclaim free space B-tree nodes, and things like that. Now, Oryx had all of this stuff before XFS was ported to Linux. XFS kept all the hooks, it just wasn't implemented. So we implemented it, and it works. We expected it to. Of course, then there was other little things like RCU-based inode lookups and stuff like that that got rid of other small problems. So now, after all of that, how does it scale? Okay. This is just the basic test box that I was using. It's a virtual machine. It's got a decent sized number of disks behind it. What I'm actually testing here is default configurations. The only thing that I've changed is that I'm using inode 64 distribution for XFS, which is typical for large file systems, and just increasing the in-memory transaction log size so that it does slightly larger IOs for the log. They're pretty much everyone sets those. We just haven't made them the default yet. So like I was saying, we're using FSMark and it's a parallel workload, and these graphs come from creating 25 million files per thread. They're zero-length files. So by the time we've got 8 threads, it's actually creating 200 million files. Okay. I chose that number rather than a billion so that this would complete in 2 or 3 days rather than 2 or 3 weeks. I didn't have 2 or 3 weeks before this talk. So, I apologise for the scale here, but the ButterFS result kind of blew things out of the water. This is creating files with FSMark in parallel. Okay. You've got red is XFS, I suppose you can all read it there. What we see here is that at 1 and 2 threads, it's pretty much the same. XFS is actually slower than the others. But the difference is when you get to 4 threads and 8 threads, XFS is showing close to linear scalability now. Okay? But we look at ext4 and it's starting to go non-linear. And ButterFS has gone way non-linear. Now, I haven't gone past 8 threads here because by the time I get to 16 threads, I've hit VFS level locks in the inode cache and the dentary cache. So even modifications to XFS make no difference there. But mind you, XFS is the only one that's hitting those locks. If you note that the XFS result there has slightly gone non-linear on 8 threads, that's because of the VFS locks. So just to show that in a different manner, this is the average rate of creation that FSMark is giving us. XFS is slower. And interestingly enough, at 4 threads it says XFS is slower than ext4. This is where benchmark numbers can be very deceiving. The actual runtime, which is what the previous one showed, XFS was running 10 minutes faster than ext4. And this is where you need to look a little bit more closely at what's going on. This is a scatter plot of the individual results for each step of the FSMark test. XFS has a very, very nice level grouping, consistent performance across those 200 million files. But if we look at ext4, it's pretty much okay, but something happens there and performance falls off a cliff. What happens? I've got no idea. I can't work it out. The I/O patterns don't change, but it falls in a hole. ButterFS, well, it's nice and fast early on, isn't it? But it's on a exponentially decreasing curve. It's not going to go any faster the more metadata you put in. So at this point, the ButterFS metadata tree is about 150 gigabytes. That's all there is in the file system. This is the problem with a copy-on-write file system. When your metadata tree gets large, every operation is copy-on-write a lot of metadata. And that's why it slows down in that pattern. It's showing how much the metadata is actually increasing and the amount of I/O that's needed for each modification. So most people won't look at this sort of data or even analyse it, but it explains a lot about the behaviours that your file system is getting. So, I mean, similarly, most people just run the FSMark create workload, but you don't just create files. What happens when you have to do a directory traversal? That's kind of important. And we see here that now, as I said earlier, the XFS metadata reads scale really well. It's significantly faster, even for single-threaded, like much faster. Same thing, but once again, you can see the scatter plots. ext4, the results aren't deterministic. Some threads run really slow. Some run a bit faster. Some are just all over the place, and then they go slow again. And note, that bit there is about the same time as on that previous create graph where performance fell off a cliff. Something went really wrong there, and it has to do with the amount of I/O needed to write directories out. Whereas you can see from all of the XFS plots, it's a nice level graph. Like I said, you can see a lot from looking at distributions of I/O. So once again, unlink. Now, unlink requires a traversal as well as a modification. Now, the traversal in XFS is very good, but as you can see, it's still slower than ext4 at even 4 threads. That's because there's a lot more overhead for doing the actual unlink. But at 8 threads, the scalability shows up again. ext4 is going non-linear, and Btrfs, well, have a look at the runtime there. That scale at the top there, that's, what, 10 hours to unlink 200 million files. Takes quite a while. XFS was about an hour. So Btrfs on these workloads is starting to show that it's an order of magnitude slower on large metadata count file systems. These are different results than you'll hear from the Btrfs guys, because they're not running these tests. They want you to hear about how wonderful it is. They don't tell you about all of the little skeletons in the corner that are getting dusty. I did warn you I might say some controversial things. Okay. So once again, you can see the effect. Yeah? ext4 is nice and fast at first, but it's got a much steeper drop-off as the thread count goes up. The scalability is not there. Okay. Now, it's interesting because at 8 threads on the unlink, you see XFS doing the same thing. It's all over the place as well. I can fix that with a makeFS option. But that wasn't the point of the testing. That's just serializing on an allocation group lock. You know, the code is basically running in parallel. The directories are over all different allocation groups, and they're lockstepping. That's all that that's saying. I just need more allocation groups in the file system, and that problem goes away. Easy to do, but that wasn't the point of this testing. Okay, so let's go back to that original comparison between XFS and ext4. So what we've got is the old XFS logging method, the new one, and ext4, and one extra piece of data, the number of IOPS required to get that performance. Now you start to see why ext4 isn't scaling. Because at 4 threads, the number of IOPS that ext4 requires to get that performance goes through the roof. XFS, it wasn't the case. The IOPS stayed fairly steady. It was bandwidth bound in the journal. And once we removed the journal, we're doing, you know, what is it there? Almost 100,000 file creates a second at under 1,000 IOPS. ext4 is getting, what, 40,000 creates a second at 10,000 IOPS. That's why X4 is not scaling. It's spraying its I/O everywhere. And if you looked at, if you paid any attention to Avi's animations of the behavior of the file systems in terms of seeks, that's the ultimate cause. That's what you saw with ext4, it was spraying its I/O everywhere. What you saw with the XFS one, where it made that nice progression, that's the effect of all the sorting we do of the metadata buffers. And you can see the effect of that in the IOP count that it's actually generating. So, I mean, basically what it comes down to is XFS isn't slow anymore. Directory and inode lookup operations are faster and scale better than ext4 and Btrfs. The Btrfs modification rate is actually limited by the metadata write-back during transaction reservation. Chris tried to fix it a bit while I was talking to him on IRC last week when I was reporting the bug that was causing Btrfs not to complete these tests. He couldn't find it easily. There's a lot of work to do to optimize the write-back. Basically, Btrfs is I/O bound, just like ext4. I'm not sure why that is. Copy on write is supposed to reduce the number of IOPS, but it's not. Okay, so in XFS land, we're all nice and happy, just like a puppy with a great big stick. Things are working and looking good. Oh, pardon?
It's a bigger puppy.
Yes. So let's just quickly pass through another look at metadata scalability. Free space indexing and allocation. We know XFS excels at this. Other file systems, well, yeah, not so much. Now, these tests are very quick and limited to 16 terabyte files because ext4 doesn't support files larger than 16 terabyte. They need another on-disk format change for that. Oh, did I put a number there for XFS? Allocating a 15.95 terabyte file on Btrfs and ext4, yeah, you're up above 350 seconds. Let me change the scale for you. Let's go logarithmic. "35 milliseconds. 45 milliseconds for 500 terabytes. 55 milliseconds for 5 petabytes. Okay? That's the nature of the XFS free space indexing. Okay? Btrfs is kind of similar. Btrfs has a problem with its in-memory caching. I'll get to that in a minute. So, X4, for orders of magnitude slower than XFS at large scale allocation. Okay? Yeah, fine. Let's use the X4 big alloc option. Okay? Brand new code. Okay? Allows us to do allocation and track allocations in 1 megabyte cluster sizes rather than 4K. Reduces the overhead by 2 orders of magnitude. Increases small file usage by 2 orders of magnitude. That kernel tree that you've got that takes 2.5 gigabytes of space now takes 160 gigabytes of space. Oh, and it's incompatible with other X4 options like not using the FlexBG option or the new online resize code. And it's not particularly well tested either. In fact, it introduces more complex configuration questions than it actually answers. Now you've got to know what your file system is going to be used for over its entire life, which most people don't know before deciding to use this. And really what it comes down to is that this is an architectural deficiency of a 1980s era file system. Free space is indexed by bitmaps. And the index time, it scales linearly with the size of modification. It can't scale to arbitrarily large files and file systems. And in fact, that generally means that the 16 terabyte file size limit is probably sane. Btrfs? Well, given that the freeing is almost as fast as XFS, it doesn't have an architectural problem. It uses B-trees to index all this just like XFS does. It's CPU-bound walking its cache. It's not been designed to scale to this sort of level. That's just an algorithmic problem, and with that fixed, it will scale just as well as XFS. It's not a big problem.
David, that's something Chris has actually got post 3.3 is the new free space caching stuff.
Yeah, I haven't tested it yet, so I'll see how it goes. Yeah. I found this when modifying XFS tests to actually test large files, ext4 and Btrfs file systems, like we do with XFS. You just allocate a huge file to consume most of the space without actually having to write it. That's where this came from. Okay, so from here, what we're looking at is that metadata scalability is good and can be considered mostly a solved problem. Further improvements will come from VFS scalability work and validating this on high-end SSDs. Yeah. But realistically, that's not the future problem. Failure, resilience, and reliability is the scalability problem. Petabyte scale file systems can contain terabytes of metadata, and we need to be able to check and repair that. How many people here have got a machine with 4 terabytes of RAM in it? Not many. Not many. When we start talking about petabyte file systems that have actually been used, that's the sort of RAM levels we're talking about to need to actually do a comprehensive check and repair on it. We need to move to online validation and repair. So, I mean, along that line, also, if we're doing stuff online already, we also need to handle transient errors somewhat better. I've already mentioned transaction rollback. I'm not going to go into any more detail about it, but transaction rollback is the key functionality that we need to add to handle errors during transactions, whether they be enomem devices, there's a multipath failover, and we've got a transient eno dev error, things like that. That'll all come into it. there's a lot of things that we need to do before that is something critical. So realistically, robust failure detection is the most important aspect of the process. Okay, metadata needs to be fully validated as correct. I mean, data validation is not something that we consider a problem that we're going to solve in XFS. XFS just gets out of the way of data. If you need to do 30 gigabytes a second of data I/O to your file system, there's no way the file system can checksum that, can compress it, can dedupe it, or encrypt it, or anything of the sort like that. We just get the hell out of the way. That's it. If you need that functionality, you either do it down in the storage array with hardware, or you do it up in the application before you start writing to the file system. It's not a file system problem. ButterFS is trying to do all this. That's a different solution. Yeah?
Parent inode pointers, are they considered a reliability feature?
I'll get to that. So, on-disk format changes are needed to fully validate the metadata. We're not going to attempt to provide forwards or backwards compatibility for these format changes. Okay? And there's a reason for that. It's a fairly significant change, and we're not going to try and do that because it will compromise the on-disk format design. So, why is it a complex change? It's because CRCs are not sufficient by themselves to provide robust failure detection and recovery. And there's not enough free space in the XFS metadata structures to put everything we need in it. Okay? There's other functionality we want to provide as well, and that requires on-disk format changes, so we may as well do that at the same time. Well, it's a flag day, effectively. So, what do we need to do? Metadata needs to be self-describing. How many people here have had their storage array write data to the wrong disk? Oh, there's a couple. How did you detect that? That they know of, yeah. That they know of. That's extremely difficult to detect, and it's even harder to work out what went wrong. So if the metadata has all the information in it that it needs to identify what file system it came from, you can immediately identify when your metadata has gone to the wrong file system. We can also detect stale metadata. How many people host file system images on their file system? VM hosting, just about everyone here probably does that. So you've got metadata from some different file system in the empty space of your file system. What happens if you trip over that because somebody corrupted a block pointer and it points to this metadata?
You get RiserFS.
Yeah, you get cross-linked file systems. Just think about that for a second from a security point of view. Yeah. So we need to have enough information in the metadata to be able to detect these sorts of problems. And that's why we need to change the on-disk format. So, file system UUID gets stamped into every metadata block. We know which file system it came from. The block or inode number gets stamped into every block, so we know that it's in the correct location on disk. That's important too. CRCs will tell us whether there's bit errors in the metadata, and that will tell us whether we can trust it or not. Okay. The owner identifier, somebody said parent pointers. The owner identifier will tell us who owns the metadata. You know, if it's a extent map for a file, the owner will point back to the inode that it belongs to. The inode will point back to its parent directory that it belongs to. Things like that. So if it does become disconnected, you can find out what it belongs to. Or even better, if you get a bad sector, you can find out what file the data got corrupted in. That's from the reverse mapping allocation B tree. So there's all sorts of things that we've got to add. And then we take advantage of that to add the dtype entry into the fields. Yeah, those directory traversals aren't using the dtype optimizations to avoid inode reads. That should make XFS go even faster on those loads. Version counters for NFS4, inode create times, increase the maximum directory size. We don't really need to do that, but if we're changing the directory format anyway, we may as well support directory metadata sizes up to a terabyte. It's just a hash define. Yeah, on that same thing, we should track the directory, tree sizes internally, rather than just the size of the directory leaves. And doing that would then allow us to do speculative pre-allocation to reduce directory fragmentation. I mean, that sounds like a good idea when you've got terabytes of directory data. And that will then further speed up your directory traversals, because it's all contiguous and the reader head will just keep hitting contiguous blocks. Nice sequential I/O for your directories without having to do anything specific. And of course then, optimizations for unlinked inodes to actually reduce the amount of overhead that we need to unlink an inode. That'll make that go faster as well. So I mean, the thing is, these are all forward-looking changes. Not everything initially will be used. It's going to take us time to implement all of these things. But once they're on disk, we can take our time doing it. We don't have to provide scrubbing straight up. We need to make sure that what we're getting on disk is correct, and we can validate it and get the repair program to do it for us. Then we can add all the wonderful features that it enables. So like I said, what can we do with this? Proactive detection of file system corruption, the scrubbers, just like ButterFS is doing. Reverse mapping allows us to locate disconnected blocks, identify blocks containing corrupted, the storage just says this disk is corrupted or this sector is corrupted. We know where it came from. Individual metadata blocks can tell us their owner, which is important for repair. And the thing is, this can all be done online. And that allows us to start implementing an online repair, very similar to what ButterFS is actually now starting to do as well. So there's all sorts of things that we can get to once we've got the information on disk. So what does it all mean? What does it all mean? Okay, so from the XFS perspective, the historical weakness is gone, metadata performance. That now scales. It isn't limited by your disk bandwidth and whatnot. Effectively now, XFS is the best scaling and best performing metadata file system that we've got. We know that the user space utilities scale better than anything else. And XFS dump is even better now, and XFS restore, because they're multi-threaded. They'll scale to as many CPUs and tape drives you can throw at it now. The feature development is going to be focused on reliability, and we're making a no-compromise approach to the improvements. Basically, XFS is well placed to remain the large and lots go-to Linux file system. That's a good thing. So what does it mean from a ButterFS perspective? Well, it's clearly not yet optimized for file system with large amounts of metadata. Okay? If you have large amounts of metadata, it's not ready for production. It will work, but it will work slowly. Okay? But that's about what we expect for a file system that's still under heavy feature development and is not really fully stable yet. Some of these things will take some time to overcome. There's a lot of locking complexity in ButterFS that may not be a solvable problem. I hope it is, but it may not be. The reliability features are already well developed. 2 slides. And it's definitely capable of supporting the expected storage that we get in the next few years. So, X4 has metadata scalability issues. They're architectural deficiencies. It doesn't handle increasing concurrency gracefully, and it isn't the fastest mainstream file system for metadata-intensive workloads anymore. There's no plan for reliability improvements apart from adding CRCs. So it's not going to keep up with where XFS and ButterFS are going. The on-disk format's showing its age, and it already struggles to handle the storage capability that we have. So really, there's a white elephant in the room here. ButterFS will soon replace ext4 as the default Linux file system thanks to its unique feature set. X4 is now being outperformed by XFS, and it can't keep up in places where XFS is strong. X4 has scalability challenges when used in current sub $10,000 servers. I mean, it's not high-end we're talking about here. Okay? And on top of that, X4 has become an aggregation of semi-finished projects that don't play well with each other. No, I did say I was going to say controversial things. So, and unlike most people think, ext4 isn't as stable or well tested as people think. There's bugs at the moment in ext4 where if you hit no space, it'll corrupt your file system. Not good. So, with the speed, performance and capability of XFS and the maturing of ButterFS, why do we need ext4 anymore?
As it says, we have time for a couple of questions, and there's a hand right down the front here.
Previously, XFS had performance problems. Now it doesn't. At which stage? At which point do we have to get? Which version of XFS do we need to use to get this good performance? How far back can we go?
Upstream, I would suggest 3.0 stable kernels, or RHEL 6.2. Everything that I've talked about is in RHEL 6.2. Yeah.
I wonder, what kind of encryption, like integrity, actual confidentiality mechanisms, integrity confidentiality mechanisms does XFS have? Like, let's say I have like a...
That's an application problem.
Well, okay, let me rephrase that question. If someone seizes my really well redundantly backed up set of data, how do you protect that with XFS?
That's a storage array problem. It's not a file system problem. If you lose your USB disk and you have not encrypted it in the first place, then you lose.
Well, sure, but...
Or your application is not encrypting the data you care about, you lose. That's not something that we do in XFS. We do not transform the data at all.
So if I use a
Decrypt?
Yeah, and that's totally fine to work with it?
Yeah.
Have you benchmarked and to see how that impacts it, for example?
Decrypt is fine for USB drives. If you want anything better that like scales to gigabytes a second like the file system does, then you need seriously expensive hardware.
Decrypt produces good native write speeds if you use AES and I.
I run it on my laptop and I haven't noticed the speed difference.
Yeah, I run Decrypt and stuff like that on my laptop as well, and it's just fine. For that sort of thing, Decrypt is what you want. For anything bigger, like you'd normally use XFS for in production, you need hardware to keep up with the rate that the file system punches data down to it.
We can shrink ext3, ext4 offline. We can shrink online ButterFS. What about XFS?
Why do you shrink file systems? Storage is cheap. XFS is for big.
Well,
add more storage.
It is about flexibility. If I created some virtual machines, like with a large...
Use thin provisioning.
But you can only change the options to XFS at makeFS files.
Pardon?
You can only change your XFS options at makeFS time.
You can only change some options at makeFS time, that's right. But things like if you're using thin provisioning, you want to use the online discard or the background trim stuff that XFS has just like ButterFS, and that will punch blocks out of your thin provisioned LUN. So, I mean, that's how you handle those sorts of problems. Just make it large and use thin provisioning.
One more. You haven't mentioned SSDs.
Pardon?
You haven't mentioned SSDs at all.
What about them?
So there's no optimizations for them? Nothing.
We don't need them.
That's a good answer. I have time for one more question if anyone... No, that's it. Okay, everyone give a big round of applause for Dave. Fantastic speech. Controversial, as you said.
That's okay.
And detailed, and we have a little present for you.
Oh, thank you.
There we go, gold-plated glass penguin with the gold from Ballarat. Thank you very much. Enjoy lunch, everyone.
Okay, so like the T-shirt says, I'm not insane, just mostly. So I work for Red Hat. I spend most of my time working on XFS and VFS level stuff, mostly in the upstream kernels. What I'm going to be talking about today is the developments that's been made in XFS scalability, mostly to do with metadata, because that's been the traditional weak point of XFS. We all know that it scales to massive amounts of data, but if you can't create that data really fast, lots of files and so on, then it doesn't really help you all that much. That's where metadata scalability comes in. Once we've gone through that, we're going to talk about what's going to happen in the next couple of years in terms of XFS development and scalability there. And really the challenge for scalability these days is reliability. And it's not performance. We fixed the performance problems. So, go back to LCA 2007 and Valorora, when she was describing when do you use XFS. If you have lots or large, use XFS. There's a problem with that though. We have metadata performance problems. This is what we're going to talk about. What are they? How do we solve them? Now we've solved them, how well does XFS scale on metadata intensive workloads? Where are we going to go from here? Being the limitation. And then of course with XFS, there's lots of locks to deal with. Okay, so really, I mean, it can't be that bad, can it? I mean, everybody says lots and large, you know. How bad really is it? So, these were taken on a 2634 kernel, single SATA drive. FSMark creating basically the same workload that Avi was talking about. FSMark creating zero-length files. One directory per file, so there's no contention at the VFS level or the file system level. Okay. Well, there's supposed to be no contention at the file system level. And what we're seeing here is the result versus the journal throughput. So our result is on your right-hand side, and the journal throughput is on the left-hand side. As we can see, the journal throughput's at 120 megabytes a second. That's as fast as that SATA drive would go. And the results scale directly with the journal throughput. So let's go to a faster drive, just to show that that holds true for even larger storage subsystems. We've now got 40,000 or 45,000. It's 7 or 8 times faster than that previous disk. Well, there should be. There's 12 disks there. Journal throughput is up at 550 megabytes a second. That's all that system was doing, was writing to the journal. Now, I know most of you don't have drives that do 550 megabytes a second. You know, so this is a big problem. And those that do have drives that have got 550 megabytes a second, you don't want the journal to be consuming that. That's just a waste of bandwidth. So let's compare that to ext4 on the same subsystem. So even with a single thread, we can see that ext4 is a lot faster. And part of that is to do with the CPU usage. Because of the algorithms that XFS has, they're a lot more complex than ext4. There has to be some trade-off for the scalability that the file system has. So any modification has to do a lot more work. And as a result, the per CPU throughput is actually a lot lower, even when there's no limitations. Now you can see this holds true. Up to 4 threads, yeah, X4 is a lot faster. 8 threads look a little bit different. We'll come back to that one. But as we saw from the previous slide, XFS is limited by the journal throughput there. Okay, so it looks pretty bad. In real life workloads, ext4 can be 20 to 50 times faster than XFS when there's file data also being written. Untarring a kernel tarball is the classic metric for this sort of thing. There's systems like a single SATA drive where ext4 takes 3 or 4 seconds to untar the kernel tarball, and XFS is taking 60 seconds. And then overwriting it, ext4 is taking 10 seconds and XFS is taking 2 minutes. It's pretty bad, pretty slow. This is the state of XFS in 2009, early 2010. Realistically, unless you have some seriously fast storage, XFS just doesn't perform all that well on metadata modification intensive workloads. Okay? And that's pretty important when you're talking about storing a couple of billion files in your file system. You have to be able to create them somehow, and you want them to be able to create quickly and so on. But, I mean, it wasn't all bad. I mean, we're seeing ext4 having some problems with those workloads as well. So some of these problems may not be just XFS, though it turns out that they were. So, the fix is in. What I'm now going to talk about is all the changes that have been pushed into the kernel since 2635 and over now to the 3.3 merge window, which has actually removed old code that some of this stuff replaced. So what we had is a major algorithmic change. Why are we changing the on-disk metadata format? That might seem a bit drastic, so we'll explain it. And then what does it all mean? Okay, so the XFS metadata problems. Metadata read scales very well in XFS. Everything is B-tree structured, so it's logarithmic lookup time. It's very scalable. However, metadata performance is just terrible. Okay? We get excellent parallelism through the metadata transaction engine, but the problem is that the transaction commit basically serializes, and it's the big problem. Okay? It won't scale past one CPU. Generally, that's because of the limitations in the I/O level, not that there's a lock in the way. We'll get to that. Because the transaction throughput, the commit, is limited by the journal bandwidth. We're writing so much information, so much metadata into the journal that will basically max out the bandwidth of any disk subsystem that you have. And that's not with data, that's with just the journal. A further problem is that metadata writeback causes I/O storms. We're modifying so much metadata and it's spread all over the disk. We then end up with random writeback patterns. 4K writeback here and then over there, and we seek the disks to death. So even if we were to fix the journal bandwidth problem, we've still then got the problem of metadata writeback